So I'm going to present our work on efficiency, fairness, and stability in non-commercial peer-to-peer ride-sharing. This is a joint work with Hun, Zong, Alex, and Fei. So first of all, I would like to give you a brief idea on what P2P ride-sharing is. So I believe ride-sharing is not new to us, but like we all know some commercial platforms such as Uber, Lyft, but P2P ride-sharing platforms is different from those commercial ride-sharing platforms in three different ways. First, like drivers have their own traveling schedules as opposed to dedicated drivers in those commercial platforms. And the central planner's objective is to maximize total social welfare instead of maximize his own revenue. And commercial ride-sharing platforms are usually they are deployed in urban areas, but like the P2P ride-sharing platforms are becoming increasingly popular in rural areas. And our paper has the following contribution to, has threefold contribution. First of all, we add user-centric features such as preferred times to the algorithm. And secondly, we proposed a novel fairness concept in an algorithm to compute fairness. And thirdly, we are the first to address the efficiency, fairness, and stability trade-off. And then I'll briefly introduce the RTV.
Sorry to interrupt, but I think your screen is not reflecting your.
Oh, sorry. Can you see my screen now?
I can see your screen, but it's not on present full screen mode.
Okay. Could you see my screen now?
Yep, perfect now.
Sorry. Okay. So now I move on to the RTV framework, which we adopt in our paper. So we consider a set of drivers and riders. Each user, which is a driver or rider, has his own feasible time window, preferred departure time, and the maximum accepted detour time. And as is a subset of riders, and the cost for each user, which is departure at time t and arrival at time t prime, has the following cost structure: the deviation cost and the time of the trip cost. And we use CDS to denote the minimum cost of a DS pair. A DS pair is the minimum cost of letting a driver D to pick up and drop off a subset of rider, which denoted as SS. So the problem of finding the optimal matching for system schedule can be decomposed to two subproblems. The first subproblem is to find the optimal driver schedule given the driver subset of rider matchings. We want to compute the best route in stopping times to serve this for the driver to serve this subset of riders. And in the second step, we want to find the efficiency maximizing system schedule. We're using the algorithm for SP1 as a black box algorithm and solve the optimal matching problem. So for SP1, find the optimal driver schedule. We first want to solve the optimal ordering of stops and timing of those stops given a DS pair. And we start with a random stopping orderings, and we then need to find the what is the, and then we use the tree search based algorithm to explore other feasible orderings, and we add techniques such as prunings and driver schedule we were using. But in order to find the optimal stopping times of given ordering, given a route, we propose a new LP to determine the optimal stopping time. The objectives contains first is deviation cost, second part is the trip cost, and the constraints are mainly feasibility constraints and constraints for some auxiliary variables. And the second step is to find a system-wide optimal schedule, and we use a standard matching problem formulation. We just need to solve this binary integer program. And now we move on to the second part is fairness. We note that in a peer-to-peer ride-sharing platform, we cannot guarantee that every rider is matched to a driver in each time. And note that P2P systems typically run over a long-term horizon. And it's good that we consider probability matching, which is what is the probability for each rider to get matched in the system. And it can also be seen as a long-term frequency of matching over consecutive days. To do this, we consider a set of probabilistic matchings and the probability of choosing one matching. And we define phi R as the probability that a rider R is matched in our probabilistic matching. And we also define a probabilistic maximum fairness, formally as theta fairness, which is we want to maximize the mean probability of getting matched in our system across all riders that can possibly be matched to a driver. And we also propose a fairness algorithm to compute fair matchings, and the cost structure is similar to what we defined above. And now we move on to study the price of fairness. By adding fairness constraint, there might be additional cost incurred, and Pareto frontier is a common tool to study the multi-objective trade-offs. And in our problem, we proved that the Pareto frontier is piecewise linear, it's convex, and also it can be computed in polynomial time. And we also formally define the price of fairness, which is the cost increase due to adding fairness constraints. And we can prove that the price of fairness has some tight upper bounds and in the feasibility region. And in the interest of time, I'm going to skip the stability definitions and directly go to the result. And so first of all, we know that we found that there exist problem instances where the price of fairness can be arbitrarily large, and the set of stable outcomes might be empty, and also the price of stability can be very large, big omega lambda times the size of the rider, and theta fair solution is not exposed stable. And we also did a numerical experiment to test our algorithm. And illustrated in this figure is our base setting. It mimics a typical morning rush hour where riders from different neighborhood, A, B, C, D, E, they depart from their neighborhood and they go to the gray star region, which represent the downtown area. And also we did additional large-scale and real data-based experiment. And here's the result. So first of all, we can see that by adding individual rationality and stability constraint, our runtime actually significantly reduced. This is because we're actually exploring less route and less possibilities by adding those stability constraints. And also we can see that the price of stability and fairness is relatively small compared to the bulk of the efficiency part. So it's good to add this additional user-centric features without sacrificing too much on the efficiency part. And also we tested our algorithm in large scale. It scales pretty well. And that's pretty much what I have. And I'm ready to take any questions.
Great. Thank you, Savannah. Any questions from the audience? If not, I just have a quick question. Could you comment on any plan for testing this algorithm in the real world?
Yes, we did. We used data from Lawrence County, which is there was a neighborhood where it's more they have the users indicated their interest in taking part in a ride-sharing for their daily trips, and we extracted the location that they indicated they want to go and their time, feasibility time, and we have one set of experiments based on that real data.